Hello students, here we have problem number 63 from chapter 7. So an inclined plane of angle theta is 20 degree has a spring of force constant K is given 500 Newton per meter fastened securely at the bottom so that spring is parallel to the surface as shown in the figure. Now the block has a mass M, is placed on the plane at the distance d from the spring. From this position the block is projected downwards towards the spring with a speed of 0.75 meter per second. By what distance is the spring compressed when block momentarily comes to the rest? So we have to find for how much the spring will be compressed. So let me draw the picture. So first of all, what we have here, we have inclined plane. In an inclined plane, we have angle theta, right? Then here we have a spring. Okay. Then here we have our box. Then it has a mass on it. Sorry, mass. Then it is at a distance of a d. Okay. It is coming with the velocity initial. The spring constant K is given. Now we have to know for how much the spring will be compressed. Suppose it comes up to here. Okay. That means we have to find X, right? Now let's write down, let's first draw a free body diagram and understand what's really happening there. The first of all, we have the weight of the box, which is mg. Now that angle is same as theta as this one. Therefore, we can say that we have a normal force here. Then if you say that this is our x, this is our y, then you can say that this force will be mg cosine theta, and that one force will be mg sine theta. Okay, so we know that our box, when it's compressed, it will be standing just here. Okay, right? So let's write down how many energies we have in initial position and also in final position. So first of all, we know that since it's at certain height, and when it will be compressed, right? This is the height. We have to draw it. Okay, so this will be our h, right? So when our box at certain height and when it has a certain velocity, then we know that we can have kinetic energy initial. Okay, since it's coming with the velocity initial, let's make it kinetic energy initial. Then what we have potential energy initial. Okay, then what we have at this point before compressing the spring, we have potential energy of the spring, which is initial, correct? It's not compressed yet, but however at this point what we have kinetic energy final, gravitational potential energy final, and spring. Okay, so and spring potential energy final. Okay, so sometimes they say potential energy as a P, or sometimes they say it's as a U. Okay, now we know that the kinetic energy, so this is our initial position, this is our final position. So we know that in the initially we have kinetic energy and potential energy, which will be fully converted when it comes to the final position. It will be fully converted to the spring potential energy final. Okay, so we can say that kinetic energy initial plus potential energy of the box initial will be fully converted to the spring potential energy final. Okay, or you can write down this equation where we have changing kinetic energy plus changing potential energy plus changing spring potential energy, which is equal to 0. Okay, or you can say kinetic energy initial plus potential energy initial plus spring potential energy initial, which is equal to kinetic energy final plus potential energy final plus spring potential energy final. Okay, now from here we can say that we have kinetic energy initial, we have potential energy initial, but what about spring potential energy? Spring initial is not compressed, that therefore we can say that it's equal to 0. Now what about final kinetic energy? We know that when spring is fully compressed, that means we're going to have a final velocity which will be equal to 0, right? So therefore kinetic energy final will be equal to 0, because when spring fully compressed, or the box will be fully stopped, which means it will have final velocity. This is 0, so therefore we can see kinetic energy final is equal to 0. What about potential energy of the box? So as I said, when it's fully stopped, you can say that this position will be a 0, okay, 0 height. Therefore we can say that potential energy final will be 0. Okay, so but when spring is fully compressed, that means the all kinetic energy initial and potential energy initial will be converted fully to the final energy of the spring. Okay, so therefore we will end up with this equation. Okay, now let's write down what is kinetic energy initial in our case. So in our case we have m v initial squared over 2 plus m g h at certain height, which is equal to k x squared over 2. Okay, now how can we find h height? We know that h is equal d plus x, okay, because this is a distance where finally it will be stopped. It will be stopped, as I said, just here. So that means d plus x multiplied to the so it will be multiplied to the cosine, it will be multiplied to the, yes, it will be multiplied to the sine theta. Okay, so you take the hypotenuse, multiply to the angle, and you will get the opposite. Okay, so that means we can come to here to this equation formula, which is mv initial squared over 2 plus mg. Now h was equal to d plus x multiplied sine theta is equal to kx squared over 2. For now, don't plug the number right now. Let's first make it simple equation, then finally we'll plug the numbers, okay? Otherwise it will be just a mess. So in this case, what we have now? Okay, so let's for now divide by m, so that we're going to have less m's. Okay, so when you divide by m, what do you want to have? You want to have a v initial squared over 2 plus g sine theta d plus x, which is equal to kx squared over 2. Okay, then what we have, let's open the bracket and see v initial squared over 2 plus g sine theta times d plus g sine theta times x, and if you're trying to bring it to the left side, kx squared over 2. Now I'm forgetting here the m, right? Divide it, we have here m, so minus kx squared over 2m is equal to 0. Now if you look at this equation, then you can see that it's quadratic equation. Okay, now let's plug the numbers. Finally, let's plug the numbers. What we have here, first of all, we have the initial velocity, which is equal to 0.75 squared over 2 plus g is 9.8 multiplied sine is 20 degree multiplied d is given, which is 0.3 plus g is 9.8 multiplied sine 20 degree multiplied to the x minus k is equal to 500. Now x is unknown, so we keep it there. Then divided by 2, mass is given, which is 2.5. Okay, so after that, when you do calculation, you will find that you will get h is equal to 0, so you will get here 1.286, I already did calculation, plus 3.35x minus 100x squared, which is equal to 0. Now if you do quadratic equation, you will find that your x is equal to, I already did it, which is 0.131 meter. Obviously you will get a second x, which is equal to minus 0.097 meters. You cannot take the negative sign, so you just cancel it, and you will find that your x will be compressed by 0.131 meters. This is how you solve such a problem.